So in this section, we'll be talking about the probability density function. And again, this is the analog to a probability mass function that we talked about with discrete random variables, but this is used for continuous random variables. So far, like I mentioned a couple times, all we've talked about is discrete random variables. That is, those variables that have just a subset of values which are clearly defined. And so we may have looked at a chart or a probability mass function that looks something similar to this, where we have all of these individual values associated with a given function, some px of x, right? That probability mass function of the random variable x. Now, for this, we said that maybe we want to assign some arbitrary a and b to our graph and find the probability that our random variable x is between the values a and b. And to do this, we would just take the sum over all possible values of x that are between a and b. And specifically, we're going to sum the probabilities, or the probability mass function, of those specific values. So we can look at a probability mass function kind of as each of these stems, each of these specific locations here just have some value associated with them, right? It's the probability mass, or the weight of each of these specific values of the random variable x. Now, we had some definitions, for lack of a better term, or some common threads that we looked at for PMFs, and that was that the PMF of x for any given little x, any possible value that random variable x can hold, must be greater than or equal to 0. We said we couldn't have any negative probabilities for a given outcome or a given specific value of our random variable x. We also said that the sum over all possible outcomes of x, so the sum over every single potential outcome of our random variable, when we sum the probability mass function, or the probabilities of each of those outcomes occurring, that must be equal to 1. And again, this follows from just our general understanding of probability that in order to define our sample space clearly, everything must equal 1, so that it's a percentage, if you will, of the sample space. So again, we said that the sum of all possible outcomes, the probabilities thereof, must be equal to 1. Now, something important, as we look at this probability mass function, some of these parts have more mass and some of them have less. So with this information behind us, we can look at the definitions that we have associated with a discrete random variable and kind of look at the analogs, or the equivalents, for a continuous random variable. Now, first we said that the PMF, the probability mass function that we've had defined here for our discrete random variables, this PMF over here, has an analog that's called the probability density function, or the PDF, of a continuous random variable. And those will often look something like this, where the PDF is ultimately still just a function, but it's a continuous function now. As opposed to having discrete values here for each possible value of x, it's now just a curve, some continuous curve, and there may be discontinuities along this curve. So for instance, we may have a curve that looks something like this, where it has a jump in it, for lack of a better term, some asymptote, but ultimately it is a curve. It's not these single valued elements that we had with a PMF. Now, similarly to a probability mass function, we also have to notice that a probability density function has a variable value. So in the case of this probability mass function, if we were to turn this into some graph, we have some value that is related to the probability at each specific outcome. Similarly, for the PDF, we have a probability at each possible continuous value. But let's look at that a little bit more. So to kind of put this in perspective, we looked at the probability that a value was between a and b of the random variable x for a probability mass function. Well, the equivalent for a probability density function is actually an integral. since this is a continuous function, we need to change our summations out for integrals. So we would take, to find the probability that a random variable x is between the values a and b, which you can see listed here as a and b, we would take the integral from a to b of this, and some new notation, little f of the random variable x. And this little f here in the terms of probability is always going to be the probability density function. So again, a little piece of new notation to add on to what you've already got with probability. But ultimately, all this is saying is when we multiply by the value, and again, this curve right here is our f of x, or the probability density function of the random variable x. When we multiply by the amplitude of that curve, or the value of that curve, and multiply that across this range, we're ultimately just taking an area. So we're looking at the area under the curve between 2 points, and again, in this case, a and b. So if we were to look at that in a slightly different way, we could say that we're just going to shade in all of this area down here. It's already been shaded, but let's shade it again. And that is the area under the curve, and thereby the probability density, or the probability of a value occurring between a and b. And that's actually where we get the probability density function from, is the fact that it's a density. It's the total area under that curve. Now, we had a couple equations over here that we said we would always abide by for probability mass functions, and we'll do the same thing for probability density functions. If we look at any probability density function, the probability density function for any specific value of the random variable x, the probability density must be greater than or equal to 0. So we cannot have any curves that extend below 0. That's no bueno. We have to keep all of those curves above the 0 line. The probability of any specific value must be greater than or equal to 0. Additionally, we must be able to say that the summation, or the integral from minus infinity to infinity of this probability density function, must be 1. So all of the area under this curve here for the entirety of our random variable must equal 1. Again, the total area under the curve for the entire random variable from minus infinity to infinity must be equal to 1. Now, kind of a weird way to look at this, but one of the axioms, if you will, or one of the rules of continuous random variables is that random variables are continuous when they are described by a PDF. So if you can describe a random variable in terms of a probability density function where this integral summation works, you can say that that random variable is continuous. Now, let's take a little bit of a deeper dive into the probability density function, and let's assume that we're interested in the probability of a very small area, and we'll call that delta. And this delta is some area greater than 0, or some value greater than 0, but it's very small. And a lot of this is going to sound like your Intro to Calc 1 course, because we're going to say, let's find the probability that a is less than or equal, or that the random variable x is less than or equal to this a plus delta. So x is between a and a plus delta. So we still have our a here, and let's assume that we add in some point right here that we will call a plus delta. And so with that, we can take this very small area here, and let's say that we're only interested in the area right there. As delta gets smaller and smaller and smaller, this is obviously much bigger than what we would usually consider delta to be, but for the purposes of illustration, we'll leave it as this. So if delta is sufficiently small, and again, I said this is going to sound like Calc 1 for a little bit, then we can assume that the value of the PDF of x does not really change. We can just assume that it's a straight line, that it doesn't have a value change. So then what we're left with is this rectangle here. So again, just assume that that's a fixed line. And to find the probability, we said that probability is a area. And so the probability density of this region would ultimately just be delta multiplied by the probability density function at A, because we said that it doesn't change from A to A plus delta. So to put that in a equation form, we can actually just write that out and say that the probability of the random variable x being between A and this A plus delta is approximately equal to the probability density function at A multiplied by delta. So again, this is just the height here multiplied by the width. So the definition of area of a rectangle. Now, something that we can look at is that as delta gets really, really small, and ultimately as delta approaches 0, then this equation right here also approaches 0. Doesn't matter what the probability density function at A is. If delta is 0, then the probability is 0. So from that, what we can find is that ultimately the probability that this random variable x, when it's a continuous random variable, is equal to any specific value, that probability is 0. Because the width of that, the actual single value of that function in a continuous random variable, is 0. Again, this is getting back to the base times height here, right? The width of that area is 0, so therefore there is 0 probability for that random variable to be equal to a specific value. Now, what this does for us is we can actually extend this a little bit and ultimately say, in this equation we have less than or equal to in two different places, and we can actually eliminate that. Because what we said is the probability that x is equal to any specific value, whatever A is, but any specific value is equal to 0. So we can actually write, and this will become more important later, but that the probability that A is less than or equal to the random variable x, which is less than or equal to b, again, that the random variable x is between 2 points A and B, is equal to the probability that x is equal to A plus the probability that x is equal to B, so these two terms here, and then ultimately plus the probability that A is less than x and less than b. So again, we're just saying that the random variable x is now between A and B, not that it is between A and B inclusive, right? So it's saying the probability that x is between those 2 points and not on those points versus between or on those 2 points. Now, the way we can simplify this even further is by saying that the probability that x is equal to any specific value is equal to 0, right? Just running back to this right here, which means that this term goes away, as does this term, because those are both single valued probabilities. So from this, we can actually see that the probability that x is between or equal to A and B is actually equal to the probability that A is just, or that x is just between A and B.